Hello, my name is Peter O'Connor from Apex. I'm a geophysicist, and the title of my paper is Hidden Limestone Landscapes, Geophysical Surveys Across the Irish Carboniferous. And my co-authors are Tony Lombard and Yvonne O'Connell, also of Apex, and I'd like to thank the IAH for the opportunity to present this to your conference. As you know, Carboniferous limestone is the dominant rock type across 50% of the Republic's land area approximately. Most of the limestones are in low-lying areas and hidden by glacial material, soil and subsoil. They only become visible through excavation, as in the case of quarries or major infrastructural developments, or by drilling for minerals or geotechnical purposes. So exposure is, in all senses, is quite limited. And this is where geophysics has a role to play. Geophysical methods are used for mineral exploration, geotechnical, environmental, and hydrogeological investigations. And there's also the ongoing TELUS airborne mapping program. Most of the surveys we do in Apex have clear outcomes and give a reasonable idea of the ground conditions, but there are some cases where ambiguity or uncertainty exists, and I'd also deal with some of those examples. And on the right, you see the Apex project map from the Apex database. The yellow dots are completed surveys, so you can see in the limestone area. Just one second while I get the laser. In the limestone Central Plain area, you can see quite a large number of surveys completed over the years, and I'll be taking some examples from these surveys and presenting them to you. And just a point that we always like to make is the integration of the geophysical data along with the geological and direct data is critical to achieving a unified ground model, that there can only be one valid ground model. And just to note that the projects are confidential. All our projects obviously are confidential, so I won't be giving any specific locations as we go along, but they're all real cases, real people. This is the only table. It's not a geophysics tutorial, but this is a quick summary of the main methods we use: VLF resistivity, VLFR, electromagnetic conductivity, EM31, microgravity, ground probing radar, GPR, electrical resistivity tomography, ERT, also sometimes referred to as 2D resistivity, and seismic refraction. And the table summarizes some of the depth ranges and the information they provide. But if you refer to the bibliography at the back of the paper, you can get some more information if you wish to investigate. Excuse me. Our first case history is a buried channel. It's in County Kildare. The setting is cutaway peat bog, overlying glacial deposits, overlying Walsortian and Allenmud limestone. And the methods used are VLF resistivity, ERT, and seismic refraction. And it's a good example of reconnaissance survey and follow-up in detail. So the site itself is pretty nondescript, just typical cutaway bog and a very flat topography and no indication of what might be underneath. This is the result of the VLFR survey. So you can see that it's quite a large site, about 1.5 kilometers by 1.5 kilometers. And the lines running in this direction, these dots are each readings from the VLFR survey. So readings every 50 meters along lines spaced 100 meters apart. And this actual contour is a contour of the apparent resistivity. So we can see this northeast southwest trending feature along the right hand side of the plot. And once we saw this feature, we had to investigate further. So we carried out some ERT profiles. And if you look at these, one second to get the magnifier up, you can see ERT profiles along here, but I'm going to show you this example here, which straddles the boundary between the low resistivity and high resistivity. So next slide is the resistivity profile 8, which crosses that boundary, and you can see the the high resistivity on the left-hand side and the shallow bedrock down to about 6, 7, 8 meters. On the right-hand side, low resistivity down to the range of the profile, which is in this case 20 meters. Further profiles using a depth range of 50 meters failed to bottom out the low resistivity. In the follow-up GI, there was a borehole drilled in the center of the low resistivity area, and it encountered limestone at just over 120 meters below ground level. So quite a significant feature both in depth and extent. And this is just a random screen grab of what the area might have looked like pre-glacial deposition, quite a large erosional channel in the limestone, uh, which are believed to be associated with the removal of the post-carboniferous sediments. It's the theory, at least, that these were extensive erosional channels in earlier times. The question then is this visible on the TELUS survey? And I had a quick, this is the 3 kilohertz EM. It seems to be this low resistivity feature running in the same direction in the middle of the plot. The next example is from the Drogheda Graben, where you have the Crufty, Mornington, Tullyalan, and Platten limestones in the area just west of Drogheda. And these examples are taken from numerous smaller scale surveys, smaller scale compared to the previous one, using VLF, EM, ERT, and seismic refraction. And again, they illustrate the rapidly changing subsurface topography. So this first one shows a drop off similar to the last one in the bedrock from about 10 meters below ground level to in excess of 25. And the second one, similarly, a very sharp drop from around 5 meters to, in this case, probably 30 meters below ground level. We have a borehole here which confirms the limestone. And one of the advantages of the work Apex does is that we almost always get follow-up information in terms of boreholes, trial pits, and even excavations. And it gives us a good opportunity to test our interpretation and refine our interpretive skills. This is just a further example. Again, rock outcrop on the left-hand side and dipping away steeply to in excess of 30 meters. Again, over a very short distance, a question of 150 meters or so. So quite a steep change in bedrock topography. And the discussion of what the original landscape might have looked like was something like this, perhaps in down from, that's the Rock of Dunamaze just outside Portlaoise. And anybody who's traveled the motorway there will be familiar with the low hills in that area, limestone hills and little valleys or depressions in between. And this is possibly what that landscape looked in pre-glacial times. And again, just a quick look at the TELUS data. It's just around this area here. We don't have data around the built-up area, but there are these circular resistivity highs and lows. So I haven't established an exact correlation, but it looks promising. The next case history is a mapping of geological boundaries. You know, the geological maps are based on interpolation between available outcrop, and in some cases, and especially in the Midlands, outcrop density can be sparse. So there's always an issue with the exact location of boundaries. I mean, the maps are very good on a regional scale, but this is an example of a site where further information was required, and a number of resistivity profiles recorded in northwest southeast direction. And you can see there's the contact here to the southeast, the Lucan Formation faulted against Namurian shales. And the example here is one of the those southeast northwest profiles recorded, and you can see the low resistivity at the southeastern end, and the higher resistivity to the northwest. And so one of the advantages of doing a couple of methods, in this case we've seismic and and resistivity data. You can see the seismic velocities here in excess of 3,000 meters. So we know this is a rock velocity. So this is a mudstone or a shale, um, and not just an increase in overburden, because the resistivities are similar to in this case. But that's why we try and reduce the ambiguity by combining a number of different methods which measure different properties. And just to go back to the map here for a second, the actual location of the boundary is the dash line here, the black dash line. So it's an offset of about 100 meters from where the actual mapped boundary is. On a regional scale, it's quite small, but on a local scale, you can see in the context of the site, it's quite significant. And this is a similar example from Kerry, where we've reef limestone and Cherty bioclastic limestone transitioning into Namurian shales again, and similar resistivity and seismic data. And again, we can see quite a clear boundary here, clear change. We have the seismic data, which tells us we're in rock here. And just going back to the map for a second, we see the actual location of the boundary. The black dashed line is about 75 meters offset from the actual geological map. So again, on a regional